All right, good afternoon, everybody. Let's get started. So welcome to 6004. Today marks an important milestone that I hope will make you very happy. This is the last lecture where we introduce new syntax. So first we learned about RISC-V on the first few lectures, and that was a lot of new syntax and mechanics. Then we had a lot of combinational logic, and now we're going to do sequential logic, and that will be it. So after this lecture, what we'll be doing in the second part of the course is essentially using the tools that we've seen so far to design some interesting digital systems, especially a processor. Okay, so in the last lecture, we started seeing how sequential circuits work, and then how to specify small sequential circuits. And if you remember, this is kind of the same flow that we had with combinational logic, where you had Boolean equations, you had truth tables, and you were able, with those two tools, to specify small combinational circuits. But then we said, okay, we actually want to build large systems, right? And the key approach, the one strategy we're always going to use is to compose smaller functions or smaller components and build them up into larger, more interesting ones. So today we're going to repeat the same strategy for sequential logic. So in the first part of the lecture, we'll see how to implement sequential circuits in Minispec. And Minispec lets you design each sequential circuit as a module, which is an entity that's similar to a finite state machine, as we saw in the last lecture. But it has some additional structure that makes it easy to compose. And we'll see that that's really important. That makes the designs very easy to compose and very easy to have large designs. Then on the second part of the lecture, we'll explore some of the advantages that sequential logic gives us over combinational logic. And essentially, this boils down to the fact that we can compute some output or some values over multiple cycles instead of just in one shot like we do with combinational logic, right? With combinational logic, we get some inputs, we produce some outputs after a certain amount of time, but that's it. And those inputs must be fixed, and those outputs must be fixed. You must have a fixed number of bits. But if you do these computations over multiple cycles, you get two key benefits. You can do both computations that produce or require a variable amount of output or input, and also you can implement computations that require a variable amount of cycles. Things like for loops that take, or while loops that take a variable number of iterations. And so we'll see how to do those in the second part of the lecture. But first, let me go back and just start with a short reminder of the previous lecture. So the previous lecture was all about introducing sequential circuits, and the first order of business was, how do you implement these state elements that we need? How do you implement these loadable memories? And so we ended up with this component, right? This 1-bit D flip-flop, DFF, which is just a state element that samples its data input periodically at the rising edge of the clock, right? So the clock is going to be some periodic signal that is going to have some rising edges, falling edges, and so on. On each rising edge of the clock, this is going to take its D input and copy it to its Q output. Now, flip-flops are the start of the show in sequential logic, but they generally need two kinds of enhancements. And so we saw those two. The first one is a research circuitry. Right, so we generally want flip-flops to start, when we power up the system, we want them to start on some known value. But remember, each of these flip-flops has a couple of feedback loops, combinational feedback loops. And what happens with feedback loops is when you power up the circuit, depending on just random fluctuations and random noise, the flip-flop is going to end up having either a 0 or a 1. And there's no way to design the flip-flop itself so that it reliably goes down to 0 or up to 1. So to do that, to set some initial value, there's a little bit of a game that we have to play when we start up the circuit. First we power up all the components, and then for the first few cycles we have this reset signal that we set to 1. And at the input of every mux, we have this. At the input of every flip-flop, we have this mux that basically says, if reset is 1, then just register the initial value that we want to have in the flip-flop. Then, after a few cycles, when all the when the power supply is at the level that we want, and we've sort of stabilized all the values of the flip-flops, then we drive the reset signal from 1 to 0, and we're off to the races, right? Then we can start doing interesting computation with these flip-flops. The other kind of circuitry is this write enable signal, because it's often the case that you don't want to update every flip-flop every cycle, right? And so we add the second max that takes in the current value of the flip-flop as one of its inputs, and then if enable is 0, it just propagates that to the input at the end of the cycle. Otherwise, it takes some other new value, right? And then we can group together these flip-flops, and this is what we call registers. And generally, you'll see registers also used for 1-bit flip-flops. So what happens in terms of nomenclature is registers can be either 1 or n bits. When we talk about flip-flops, we're generally referring to 1-bit elements, 1-bit state elements, right? So this, instead of having a single bit input and a single bit output, has an n-bit input D and an n-bit output D, and it's just multiple of these flip-flops in parallel, right? Okay, so once you have these registers, we said, look, there are many ways to implement a state and sort of organize, how this state gets updated. But we're going to do, the most straightforward and most common way of designing sequential circuits, which is what we call synchronous sequential circuits. So we're going to have some registers. And they're all going to be driven by the same clock signal, right? So they're all going to update their contents at exactly the same time. And by doing that, we can discretize time into cycles, right? We can just think about, instead of what happens at this particular picosecond in the circuit, we can think about what the circuit does in each particular cycle, right? So the same way that we discretize voltage levels with the digital abstraction, now we're discretizing time by breaking it up into fixed size chunks of time called cycles, right? And that's sort of the period of your clock signal, right? So then we can model all sequential machines, or all synchronous sequential machines, as what we call finite state machines, FSMs, where essentially you have some registers that return k bits or give you k bits of state, and then you have some blob of combinational logic that does two things. First, it takes this state and also some n bits of input, and then it computes two things: the next state, which it then feeds to the registers, and also some output, some n bits of output, right? And by just taking out time, or taking time out of the equation, we can use things like truth tables that describe the next state, right, or these outputs of the combinational logic, both the outputs of the circuit and the next state, as a function of the inputs, right? And that just gives us our precise specification of our sequential circuit, right? And so we can use truth tables. We can also use state transition diagrams, which Silvina introduced in the previous lecture, right? Which, remember, this is an example state transition diagram where you have states. Each of the states is shown as a circle here. The first, or the initial state, is circle in bold to denote that that's where we want to start. And then we have arrows to denote transitions between states in response to particular input values, right? Okay, any questions so far? So now I have this wonderful abstraction, right? And in theory, all we have to do is take this combinational logic and just design this giant blob of combinational logic and be done with it, right? A processor is just a bunch of registers, right, with a large amount of combinational logic. Now, the problem is that FSMs, as nice as they are as an abstraction, they're not very useful to build circuits. The reason is that we have more structure in our circuits than just one blob of combinational logic that takes all inputs, computes all outputs, right? And even worse, the problem is that FSMs don't compose very cleanly. So again, what we want to do is build large sequential circuits from small sequential circuits. When we had combinational circuits, we abstracted combinational circuits as functions. And that way we guaranteed that the composition of different function calls, was acyclic, right? You need to have the arguments in before you get the outputs out. But that's not as easy with finite state machines, so we're going to need to do something different. And just to show you one very simple composition that results in a cycle, suppose that you have some FSM S here. This is a register R and an XOR gate. This has a single input and a single output, and the FSM just takes the value of R, XORs it with N, and outputs it here. And then we have some outer FSM that takes this output, negates it, and sets it as the input. And because you have a combinational path from the input to the output and from the output to the input, now you have a cycle. So in code, this would look something like this, right? You have an inner FSM that has a register and has an output and so on. And then you have an outer FSM that instantiates this inner FSM, right, and sets s.in equals not s.out. Well, actually, it should be equals not s.out, not equals s.out. Sorry. So the problem, actually, most hardware description languages work this way. In particular, Verilog, System Verilog just tell you, hey, here's some syntax to describe some structural collection of FSMs. Wire them up however you want. And if you get a cycle, Now you might think, well, if you get a cycle, I'll definitely get a compiler error. You'd be wrong. Right? Just read this article if you want to learn more, if you're curious about the horrible ways in which Verilog will do whatever it wants whenever it gets a cycle. And so, this makes all sort of the Verilog family of languages quite hard to use. And in fact, this article explains what companies do in practice is they build their own custom languages to trim the edges, the rough edges of Verilog, which is really not the way to go. But the other hardware description language that does very well in this department is Bluespec, right? So the claim to fame of Bluespec is that you can actually take multiple sequential machines and then combine them in very fancy ways. So Bluespec gives you, fairly detailed semantics. It essentially gives you atomicity guarantees. It gives you serializability guarantees. It gives you, a bunch of concepts that are essentially the hardware equivalent of having a transactional database. If you don't know what a transactional database is, well, you're going to need to learn a bunch of concepts to use transactions correctly. There's a lot of it's a very powerful abstraction, but it takes quite a while to learn, right? And so what we've done with Minispec is essentially to take all of that complexity out. That basically took us 4 lectures to explain. And so we're going to do it in half. And essentially what Minispec does is something very simple. It's, how much structure do I need to add to FSMs to make them compose? So let's see that. So what Minispec does is it imposes a little bit of structure over this blob of combinational logic. So instead of having a single chunk of combinational logic, you have 2 types of combinational logic. You have what we call methods that produce outputs based on some input arguments. So methods are just like functions. They take some arguments. They can use the current state, the current state of the output of the registers in the module, and then produce outputs. And then you have rules, which are a separate blob of combinational logic that take the current state, take some different inputs, and then compute the next state. And they don't compute outputs, right? So essentially what we're doing is we're splitting the computation of outputs and the computation of the next state. Methods compute outputs, rules compute the next state, and they use different inputs. And it's not obvious why this actually composes. We'll see in a bit when we start combining modules why the composition guarantees are very clear. Okay, but before we start composing modules, let's design a basic one. So, just as a reminder, this is the 2-bit counter example that we saw last time. We're gonna start, our first task is going to write this as a Minispec module. So remember, this had a 2-bit output, a 1-bit input, and we could describe it with a truth table or also the state transition diagram, right? So remember, this had 2 bits of state, so 4 possible states, and if the increment input is 1, then it transitions from 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, and then if the increment signal is 0, then it stays on the current value, right? So more sort of pictorially, the circuit is going to look something like this, right? We have some module named 2-bit counter that has a 2-bit output called count, and this inc input that's a single bit, and it then has some reset and clock signals, right? Now, how do we go about implementing this? Well, last lecture, Silvina showed you an implementation. I'm going to show you a slightly different one, which is, this is the same circuit we saw, but it's drawn a little bit differently. So first we have a 2-bit register, right, that stores the count. You see that this takes 2-bit, produces 2-bit outputs and takes 2-bit input. Now the next thing we want is, this is the state. This directly encodes the state. And so we have some reset circuitry because we want this to start in state 0, 0. So what we're going to do is have a reset max here, and then if reset is 1, we're just going to store 0 in our register. And then once we're not resetting, we have yet another max here. That's the write enable signal, or the write enable circuitry. And so we're gonna update this register with one of two values, right? So if inc is 0, we want to retain the current value. So we take the current output, just feed it back to the input. Now if inc is 1, we want to take the current input, compute this input plus 1, right, and then produce a 2-bit value, then we feed back to the input of the register. And so at the beginning of the next cycle, or at the end of this cycle, this register will sample its own value plus 1, and then it will propagate it starting on the next cycle, right? Now, Silvina went ahead and derived all the equations for how do you do plus 1, and yes, it's a NOT gate and an XOR gate, and you can go and do that, but that's, in this lecture I want to sort of raise the level of abstraction a bit, and this is just a circuit that computes plus 1 for a 2-bit value. Any questions? Okay, so let's go ahead and see how we implement this in Minispec. So first, you have this module. So we start by just wrapping everything in a module, and we give it a name. The name must be uppercase. We're going to call it 2-bit counter. The first thing that we usually do is declare our registers or state elements. And so this follows a syntax that's very similar to what you see in Java or C or Rust or Go. A little bit different from Python, but it's not hard to, after using it a couple of times, to see what's going on. So what is this saying? This is a fair amount of syntax, but it's saying please instantiate a register. This is the reg module that stores values of type bit2. Right, so this is saying I want a 2-bit register that's named count, and that takes one argument, which is its initial value. So I want this register to be initialized to 0. Right, so this instantiates a 2-bit register named count with initial value 0. What's the next thing that we have to do? Well, produce the output. So we can write this as a method. Right? A method is just combinational logic that computes the output. And so this is just, in this case, it's very simple. We can have a method that returns a bit2 value that's called getCount that just returns count. We say equals count. In general, methods can have arguments. In this case, this method does not have any arguments because we don't need any input to produce this output. Then we have an input called inc of type bool. That's fairly self-explanatory. And finally, what we need to do is compute the next state given the current state, right? And that is what a rule does, the last big element of modules. In this case, we're going to have a rule that's called increment. This is just like a function or a method, right? You can have a sequence of statements, but there are no inputs. And this rule fires automatically every cycle. It's going to execute every cycle, right? You don't have to call it. You don't have to do anything to invoke it. It's like, the module has a life of its own, right? And it's going to compute the next state based on whatever inputs you set. And, in this particular cycle, it will just execute once. And so what this rule is saying is if the inc input is set, right, is set to true, then write count plus 1 to count. Right, or store the value of count plus 1 into register count. And it is using this weird assignment thing that we call a register assignment. This is different from a just equal sign, right? It's like arrow equals. And that has some important differences, which we'll see in the next slide. So we're going to be very careful about distinguishing between variables, for which we use combinational assignments, just equals, and registers, for which we use this type of assignment to do a register write. And that's because there are some important differences. So let me just spend a couple of minutes describing what registers are in a little bit more detail, right? So we've seen this in action a little bit, but just to emphasize the point, this is a parametric module, and yes, modules can be parametric, and you can define your own. But I won't go into that in this lecture. You can see the tutorial for details. And so, for example, you have reg. You can have a reg of bool, right? This is a register that stores a Boolean value, or a register of bit 16, which is a register that stores 16-bit numbers. But you shouldn't write reg of 16 because 16 is not a type, right? So this is a common mistake. So if you want to store 16-bit values, it's reg of bit 16. And you can have any other type, an enum, a struct, or what have you. Now, the other important thing is register writes use this special register assignment operation. So you write, count arrow equals 1, right? Not count equals count plus 1. And this is because there are two key differences. The first one is that this register assignment updates the register at the end of the cycle. What this is saying is take this and put it at the input, at the D input of this particular register. Put this value at the D input of this particular register, right? And that is the key difference. Equals, the variable is updated immediately, right? You see the new value anytime that you read the variable anytime later in your code. That's not the same with register writes. And then registers can be written at most once per cycle. So if you don't write to a register, it will retain its own value. If you write to a register, it will update itself. But if you write twice, the compiler will give you an error. Okay, so let's see this in a little bit more detail. Let's go back to the example, the 2-bit counter example, and I have a little demo here. So this is the same code that we've seen. And the advantage of writing this is that can run it. So this is valid. We don't get any errors, and then we can synthesize it, just like we synthesize functions. Right now, you can say take this module, synthesize it, and also visualize it. And so you can see that this will produce sort of the picture that I showed you, right in the example. So you have two flip-flops here that store bit 1 and bit 0 and bit 1. You have this get count output, this 2-bit output that just takes the outputs of these flip-flops, right? And then you have this increment input and the reset input, and there's a bunch of gates that, based on the increment input and the reset input, determine the values at the inputs of the flip-flops for the next cycle, right? And of course, both flip-flops are driven by the clock signal. Now, you see that there are two inputs that don't show up in the code, and these are the clock and the reset. And that's just convenience, right? We're going to have circuits with clocks and resets, but you're not going to see these in the code. There's no clock input here. It's automatically generated. Okay, the other thing is we haven't seen any method with arguments, but let me just show you. And by the way, this is equivalent, this syntax, if you don't know about it, we could write the following: return count and method. These two are equivalent, but for very short methods, it's nice to just say equals. It's a shorter way of expressing what the method does. And you can use that same syntax for functions. Now let's write a method that takes in an argument. So for example, let me write a method called countIs, where we pass some bit to input x, and then we say, this is going to return true if the count is x and false otherwise. So we can just say count equals x, and that hopefully works. Yes. So now note that this method has an argument, right? Unlike the getCount method, which doesn't. And the way this shows up in the circuit is you see that there is this new input, count is x. There's a bunch of logic that will take the current state, the argument, and then will give you the output count is. Right? And then, of course, we have the previous circuit, exactly the same circuit as before, right? With get count, clock, inc, and so on. Okay. Any questions? So you can see that this is a fairly straightforward way of specifying what a sequential circuit does, right? Now, let's get to the main point here, which is why are we dividing this chunk of combinational logic in FSMs into methods and rules, or into one method or some methods and a rule. And the reason, as I mentioned before, is that now we can compose modules. So now, let's say we have our 2-bit counter module, and we want to make a 4-bit counter module out of two 2-bit counter modules. Well, how can we do this? Well, you can have two submodules called lower or upper, and so this is just going to use the lower 2-bit counter submodule to store the lower 2 bits of its 4-bit output, and then the upper is going to store the upper 2 bits of its 4-bit output. So given that the lower's count is the lower 2 bits and upper's count is the upper 2 bits, it's pretty easy to write the get count method, right? It's just the concatenation of upper and lower, right? So this is 2 bits, this is 2 bits, this is 4 bits. We're concatenating two 2-bit values. So far, so good, right? Okay, we're still going to have an increment input, an inc input bool. And then the rule is going to do something different. So here we don't have registers. We have submodules. We have these two instances of 2-bit counter. And these don't have, we can go and manipulate the internal registers of the modules. Instead, what we're going to do in the rule, which remember, the whole purpose of the rule is to compute the next state, right? And the next state, to compute the next state, when we have submodules, what we have to do is set the inputs of the submodules. And then the submodules themselves will set whatever registers they have internally, right? So how do we, this gets to the key point here, which is if you have two 2-bit counters, how do you build one 4-bit counter? Well, so you can have the lower counter, the lower 2 bits, increment every time that your increment input is set, right? So lower.inc is just inc. And then how about the upper one? So for the upper 2 bits, you want to increment the upper counter if you itself need to increment, and the lower counter is about to wrap around. It's at its maximum value, right? Because then it's going to go to 0, and you would like to increase your own, the next 2 bits by 1, right? So then this is going to be 0, 0, 1 to 3, and then this will get to 3, this will have 0, and then the next cycle inc is set to 1, this will go back to 0, but this will be 1, and so overall our output will be 4, right? Okay, so now we have this increment rule that sets the inputs of the submodules. It's not writing to registers, it's just setting inputs. The way this works is, now you have different modules and you have these rules that fire automatically, and it's important to understand in what order do they fire, right? What order do they execute in? And the semantics here are very simple. What's going to happen is the 4-bit counter rule is going to fire. It's going to set the inputs to the rules of these two methods, right? Of these two submodules, and then the rules of these two submodules are going to fire, right? So rules execute outside in, from outer modules to inner modules, and that's it. Okay, any questions so far? So let's just draw a more general picture, right? We started with this picture of a basic module that just has registers, and then we say we split this blob of combinational logic into methods and rules. And then the more general submodule is something like this. Now it looks kind of scary because the submodules are here and the registers are over there, but it's actually very similar. The methods take arguments and compute outputs. The rules take inputs and give inputs to the submodules. Both the methods and the rules can call methods of the submodules. So that's the argument output that you see here, right? You have seen this already, right? You see that here we're calling, in this method, we're calling the methods of upper and lower, and in this rule we're calling the lower.getCount method, right? Okay, so now that we have this sort of general module picture, we can summarize all the components and what each component of a module does. So we have submodules, which can be the registers or other modules, so that you can compose modules using submodules. You can have methods that produce outputs giving some input arguments and the current state, but do not touch the next state and do not set inputs. You can have rules that produce the next state and submodule inputs given some external inputs and the current state, but do not produce outputs. And then you have inputs, which are these external inputs controlled by the outside module that are then fed to the rules. Okay, so that's a lot of syntax, but and so over time, you'll get a lot of practice with this. And believe me, this might seem like it's a little bit complicated now. It will not take you a long time to get accustomed to writing modules. Also, we're going to limit the kinds of composition that we have in 004. We have what we call strict hierarchical composition, which is sort of formalizing the picture that I showed you in the previous slide. First of all, each module, we're going to impose two restrictions. The first restriction is each module is going to interact only with its own submodules. The second restriction is that methods will not read inputs, right? So only their own arguments, but not the inputs that are used by the rules. And if you do that, you get two nice things. The first one is there are no combinational cycles ever. The second one is that you get these nice composition semantics, that rules fire sequentially from the outer modules to the inner modules. So the system behaves as if you have this very predictable order where things are happening, even though in fact you have a bunch of parallel logic, right? And you have a lot of parallel actions going on. Okay, there are ways that you can compose modules non-hierarchically. We will not use them in this course. So you can, if you're curious, you can see the reference. It is out of scope. So one last bit of syntax, and then we're done, is how do you simulate and test a module, right? And this is just like with software development. You want to, as you're developing modules or as you're developing components, you want to test them and figure out that they do what you expect them to do. And some hardware description languages are actually not very good at this. So in the old 004, when students did their own processors, we didn't have tests for the components of the processor. They just built their own giant processor, and then we had this super long, very carefully constructed program that took the processor through a sequence of very carefully constructed instructions, right? And over thousands of cycles, you would basically, open up this visualization tool that had like hundreds of waveforms. It would just show, what happens to every signal on every cycle, and then, you take a look and say, okay, at cycle 117, right? This input doesn't do what I expect. And that's kind of hard to debug if you have like hundreds or thousands of bits, right? Who debugs their programs by building a giant program and then visualizing how all the signals change every cycle or change over time. Now this thing worked because we had Chris Thurman. Chris Thurman was in charge of this course before, and Chris is awesome. And so the way this would happen is he would go to lab, and students would say, well, at cycle 117, this weird thing happens, and he would immediately say, well, it looks like the upper bit of your less than comparator is actually returning the wrong value. This, not looking at the student's code, right? Now, this would immediately prompt the student to say, "Wow, right? How did you know that, right?" And the point here is that this approach works as long as you have Chris, as long as you have someone who has 40 years of experience of helping students debug their own processors, right? But in real life, it's going to be you against bugs, hopefully your own bugs, even worse, other people's bugs, and unfortunately, you're not going to have Chris Thurman by your side. So you need to get into the habit of writing your own testing modules, right? And so the way that we do this is by writing what we call test benches. So a test bench is another module just more sequential logic that uses the module we want to test as a submodule, sets its inputs, checks its outputs. That's it. And to do this, this is one example. Let me actually just show you a quick demo of this. But to do this, we are going to need a little bit of help from the language in the form of what we call system functions, right? So here's our 4-bit counter that we've built with two 2-bit counters, and then we have this test module, 4-bit counter test. Now there are two things that we can't do in normal modules and that we can't do in hardware. We can't produce, print things, and we can't sort of stop the clock or stop the world. And so this is, in test bench modules, we're going to have what we call system functions that are going to do just that. We're going to use display to print things, and then finish to control the simulation and just stop the simulation. So now you can compile this and run sim 4-bit counter test, right? What is this doing? Well, each cycle, this is saying, well, on odd cycles, set increment to true, otherwise set increment to false, right? It has this 4-bit counter module, and then every cycle is just going to print the current output, and it's going to check that it's what we expect. And if after 32 cycles we get what we expect, then we're going to declare victory, right? And so here's the output of this. So you get cycle 0, counter get count is 0, cycle 1, counter get count is 0, but here we're setting the increment input, so at the next cycle you get 1, and so on, right? And so this goes all the way up to 15, and it wraps around to 0, and you can see that yes, the 4-bit counter actually works as we expect, right? If we go and mess things up and say lower count upper, right? Hopefully this test will fail. So yes, right? Count should have gone to 1, it goes to 4, we find that, and this prints fail, wrong count. Okay, any questions so far? Good. So that's it for syntax. Now, let's in the rest of the lecture, let's spend some time looking at some of the advantages of sequential logic over combinational logic. This boils down to the fact that time is more flexible than space. What does that mean? Well, what that means is that with sequential circuits, we can perform a computation over multiple steps, over multiple cycles. And moreover, that number of cycles can be variable. And that gives us two very important advantages. The first one is that we can now solve problems that require both a variable amount of input, or either a variable amount of input, or produce a variable amount of output. The second thing is that even for problems that take a fixed amount of input, let's say 32 bits, and produce a fixed amount of output, let's say 32 bits, there's no efficient way to implement them with combinational logic if they require a variable number of steps. And so with sequential logic, we can address that and essentially implement all those computations efficiently. Let's see a very simple example that sort of emphasizes this first point, the variable amount of input and output. So if I ask you, build me a circuit that adds two numbers of arbitrary length, right? With what we've seen with combinational logic, your answer should be no, I can't, right? I can build you a circuit that takes in some number of bits, right, and adds them up, but it's going to be a fixed number of bits, right? You can't build me a single circuit that does both, 1 bit and 4 bit and 1 billion bit addition if that circuit is combinational, because you need to do that addition in one shot, right? You get all the bits of the input, you produce all the bits of the output after some time. But with sequential logic, this is actually really easy. If you think about it, this is just how we do it in our heads, right? If I show you, some giant string of numbers, right, that goes all the way, this could be 1 million digits. Can you do this? Can you add them up? Well, sure. Right? All you're doing is adding one digit at a time, right? You start here, you compute the carry, you go do the next one, compute the carry, keep going, right? Eventually, you'll get your output. And so how do we do this with sequential logic? Well, let's just build a circuit that does one digit addition, or produces one bit of the output per cycle. So what is that? That's a full adder. And then as inputs, we're going to take A and B. And then what do we do with the carries? Well, the carry in, instead of coming in from an input, we're going to remember the carry out from the previous cycle. And we're going to do that by having the carry in be the output of a 1-bit flip-flop, and then just feeding as an input the carry out. Right? Is it clear why this works? Let's see some waveforms, right? Like if you see this circuit, you should be able to say what happens to the output over multiple cycles if I set the inputs as I want, right? So what happens is, this is cycle on cycle 0. So remember, this is the clock, goes up and down. Cycles are the time intervals between rising edges of the clock, right? So this cycle begins here, ends here. This cycle begins here, ends here, right? So in cycle 0, we feed A0 and B0 as the inputs A and B, and then we have, let's say we have 0 in Cin and as the state of this flip-flop, and then we get the first bit of the sum, right? Some propagation delay later, we get the first bit of the sum at this output over here, right? Then next cycle happens, and what we do is we feed this circuit A1 and A1, and in cycle 0, this circuit also computed C1, which is now at the output of the flip-flop. It is now Cin. So now we have C1, so we get A1 plus B1 plus C1, that's S1. Right? Cycle 2, we feed it A2, B2, C2, get S2 in the output. You want to add 16-bit numbers? Just do it over 16 cycles. You want to add 1 billion digit numbers? Just give it a billion cycles, right? Any questions? Great. So you can trade space for time, and if you have variable inputs and outputs, you can actually solve problems that we couldn't solve before. Let's see the other side of the story, right? The circuits that require, or the procedures that require a variable number of steps. So we're gonna build a circuit that computes the GCD of two numbers. The GCD is the greatest common divisor, right, of two numbers A and B, and this Python code over here shows an implementation of one way to do this efficiently, which is Euclid's algorithm. Now, the way Euclid's algorithm works is you have two values x and y, which you initialize to A and B, your initial inputs, and then while x is not 0, you do one of two things. If x is greater than y, then you subtract y from x, and otherwise you swap x and y. Okay? So once x is 0, the GCD of x of A and B is in y. Let's see one example of how this works. So suppose that I want to compute the GCD of 15 and 6. So I will first set x to 15 and y to 6, right? This is what I do in these two lines of the code. And then I'll go through multiple iterations of this loop. Is x not 0? Yes, okay, so we have to execute an iteration of this loop. So if x is greater than y, we need to subtract. Is x greater than y? Yes. So we need to compute x minus y. So we do subtraction, and then we end up with x equals 9, y equals 6. Now, next iteration. Is x greater than y? Yes, still greater than y. So we do 9 minus 6, and we get 3. Now, for the next iteration, is x greater or equal than y? No, right? 3 is smaller than 6, and so we need to swap. So now we have 6, 3. Then we subtract 3, 3, subtract 0, 3, and now we're done. Right? And so the output is in y. This is the result. And we know that we're done because x has become 0. Right? Okay. Any questions? Okay, so this is a fairly simple algorithm, but we know how to write this in software, in Python or in C or in whatever. How do you build a circuit for it? Well, our strategy here is going to be pretty simple. We want to, because this takes a variable number of steps, we're going to build a sequential circuit that performs one iteration of this while loop per cycle, right? So in this case, we take the 6 iterations. In other cases, with other inputs, we can take hundreds of iterations, right? So we'll just build a sequential circuit that way. Instead of showing you the code for the module, we're going to go the other way. First, I'm going to show you the circuit, right? We're going to build the circuit. And you can do this quite systematically. There's a method to the madness here, which is to say, okay, first of all, what are my state variables, right? If I want to do things over multiple cycles, what do I need to remember? Well, in this case, it's pretty clear that you need x and y, right? You're using them on each iteration of the loop. So we're going to have 2 registers, x and y. Now the next thing is, on each cycle, what do I need to compute from x and y? And if you go to the code, you'll see that you need to compute a few things, right? First of all, you need to figure out, is x equal to 0, right? So you can have a comparator with 0 here that will give you a 1-bit output saying, is x 0, right? And that's to figure out whether you're done or not, for example. Then, if you are not done, you need to figure out, is x greater or equal than y, right? So we can have a greater than or equal comparator that takes as inputs x and y, and then it gets as this Boolean output as the result. Yes? Okay. And then if x is actually greater or equal than y, we need to compute x minus y. And for that, we can just have a subtractor circuit that takes x and y as the inputs, and then we'll get x minus y as the outputs. So now we have all the main chunks of combinational logic that we're going to need, right, that do all these operations every cycle. The next step is to see how the state evolves, right? So there are 4 things that we want to insert or to set x and y to, depending on where we are. Right? Let's start with at the beginning. If we just want to start the algorithm, we're going to set x to a and y to b, right? And so because we want to set multiple things, we're going to have a max at the input of each of these, and then we start sort of filling in the inputs. Now, let's say that we're in the middle of the while loop. There are 2 things that can happen, right? If x is greater or equal than y, then we need to store x minus y into x and y into y, right? So y doesn't change, but we need to store x minus y into x. What's the other branch of the while loop? Well, that this condition is false, right? And so if this condition is false, we need to swap, right? So x samples y, so x stores the current value of y, and y stores the current value of x. Finally, if we're done, right, if we don't have anything else to do, that is, if x is 0, then we just need to retain our current values, x and y. Okay, so we have a max with 4 inputs, and we're almost done. The only thing that we need to do is derive the logic that for the select signal, right? So what we're going to do is we're going to have a start, a 3rd input called start that tells us, when do you want to start. And then the select signal, is just a chunk of combinational logic that uses these 2 inputs, right? To see, do we need to start? And if not, are we done? And if not, do we need to subtract? Or do we need to swap? Right? And so I'm not going to draw the gates, but this is this very simple expression, which is just a couple of maxes, right? Okay. Any questions? So now you have a procedure for going and drawing a sequential circuit. We've translated Python into hardware. Isn't that cool? Now let's write it in Minispec. And this is actually also pretty simple because it maps very well to the Python implementation, right? Rather than drawing circuits, you can say, okay, well, first of all, let's work with words, which are going to be 32-bit values, so I can just type def that. And we're going to have registers x and y, which are going to take some initial values. 1 and 0 are nice because then the circuit just stays in some state that's not done, but that also doesn't ever become done. We have three inputs, start, A, and B, as we saw before. And then we have a rule that computes the next values, right? So if start, then we set x and y to A and B respectively. Then if x is not yet 0, this is one iteration of the loop, right? This is exactly one iteration of the previous loop that we've seen in Python. If x is greater or equal than y, then we store x minus y into x. Otherwise, we swap x and y, right? Now, the one final thing we need to do is give some output, right? So in this case, the output is not going to be it's not going to be valid for a while. So we're going to have two methods. One that just returns y, but then an isDone or isValid output method that says, here's when you can actually use this result, right? And so the way this module works is you set, whoever's using this module sets all these three inputs in some particular cycle, sets start to true, sets A, sets B. Then this module starts computing the GCD of this over multiple cycles, and then when it's done, it will output, it will set isDone to true, and then it will give you the value that you want, the GCD of A and B in the output, right? Okay. We're going to stop here. There is one minor detail here, which is that the interface of this module is a little bit off. It is easy to misuse. And so in the next couple of slides, which you will see in recitation, and you'll see several examples of how to use this, you'll see that basically, because you have multiple inputs and multiple outputs, it's easy to forget, for example, to check the valid bit, right, and then get the wrong result. And so you'll see a way of avoiding this, which is with a new type that we call a maybe type. But there's a general rule that you should always follow, which is that if you have related inputs and outputs, and this is true of software and hardware, this is true pretty much everything, right? Interfaces, right? Inputs and outputs are like the attack surface of your module or your thing that you're designing. You want to minimize that. You want to make it very hard to inadvertently do the wrong thing. And so the general rule here is group-related inputs and outputs. So instead of having three inputs and two outputs, we should have one input that is either invalid or valid, and one output that is either also invalid or valid. And then with that, I'll leave it there, and you'll see, the type. There's actually a built-in type that lets you express optional values, and you can see over the next two slides how that results in a simpler implementation of GCD. That's it for today. Thank you.